Hello, this is Teach Nichols, and this lecture is on light interference. So just like all other waves, the superposition principle can apply to light. This means that if multiple light photons arrive at your eye in phase with each other, which means they're both cresting at the same time, your eye is going to interpret that as constructive interference, lots of light, and it's going to look bright. On the flip side, if two light photons arrive at your eye in opposite phase or phase shifted 180 degrees, your brain interprets that as no light at all or dim or dark. There's lots of examples of physical phenomenon in the world that produce what's called an interference pattern with light, where we see this constructive and destructive interference. You've probably witnessed some of these things. The one on the far right, of course, is an oil slick on a puddle. You probably thought oil was just colorful. It's not. That's actually caused by destructive interference of light. Oil itself is sort of clear or slightly brown. But those colors are coming from the interference. Another interesting example is the picture on the far left. That is called a Poisson's dot, and it is in the very center of a shadow of a tiny ball bearing. It turns out there's always a bright spot in the center of any shadow. You don't notice it when the shadow is of an irregularly shaped object, but if you set up the experiment really carefully, you actually can get this bright spot right in the middle, which is caused by light interference. For the rest of the video, I'm going to focus on one specific type of interference called diffraction. And we're going to start with two-slit diffraction because I think that's the easiest one to understand, partly because we did an example of this in class with two speakers that were creating sound waves and creating constructive and destructive interference in the space around them. Two-slit diffraction for light works the same way. We have a light source that's hitting a barrier that has two slits cut into it. And on the other side of the slits, the light wave spreads out as if it's sort of two new light sources. And where those crests and troughs of the light waves line up in the space beyond the screen, we find constructive and destructive interference as represented by bright and dim areas of the light. If you set up a projector screen at some distance away from the barrier, you find a series of bands of bright and dark light that correspond with this interference. In the center is a very bright band called the central maximum, and we number or order the bands away from the central maximum, starting with m equals 1, m equals 2, and so on till infinity. Of course, in between each of those bright maximum locations is a dim spot that is exhibiting destructive interference. There is an equation that explains why we have constructive interference at each one of these special locations marked on that drawing. The reason is because the waves, as they spread out from the slits, have to travel a different distance to get to different spots on that screen. At the central maximum, both waves have traveled the same distance because it's right in between the two slits. And that means that since those two waves were in phase when they passed through the barrier, they're going to be in phase when they arrive at that location, and therefore we have constructive interference at that location. The way that equation sort of works is that location is identified as m equals 0. It's the center. And the delta D represents the difference in the path length of those two light rays, right? They traveled the same distance, so delta D is 0 for the central maximum, and therefore that equation basically says 0 equals 0 for that location. However, as you move outwards to the different M spots, you'll notice that the light rays passing through the gaps have to travel a different distance, right? Whichever gap is closer to the bright band, the light ray doesn't have to go as far. And so if you picture these two light rays like being sort of like bent away from those slits, you can imagine that at some point they get out of phase and then they line back up again when the wave that's got to go further travels exactly one full wavelength longer than the wave that is closer. So in this equation, it basically says we're going to have constructive interference when the difference in the distance that those two waves have to travel is equal to any number times the wavelength. So for m equals 1, the longer wave goes one wavelength further than the shorter wave and they line up. For m equals 2, the bottom or longer wave is going to go 2 wavelengths further and they're going to line up again. Just as a point of clarification, the dark spots are going to be caused by 100 degrees phase shifts. In other words, we're sort of a half of a wavelength difference in the distance traveled, and that basically causes destructive interference when a crest lines up with a trough. So there is an equation that can be used to roughly approximately calculate the locations of those bright spots on a screen past a two-slit interference situation. The variables that are going to be relevant in this relationship are the wavelength of the light, or lambda, the slit spacing, so how far apart the two barrier slits are, or D, the distance to the screen, which is L, and then of course, Y max is the Y distance from the central maximum to the next maximum. So it's called the maximum distance, basically, at any given M value that you are interested in solving. So it would be great if you would pause this video and do a short little thought experiment with yourself and think about how even one of those variables is going to affect Y max. So in other words, if lambda or D or L goes up, do you expect the distance to the first dot from the central maximum to go up or down? So go ahead and pause for a second. If you can come up with at least one linear or inverse relationship, it'll help you to make sense of this equation when we get it. All right, so Y max has a linear relationship with lambda. In other words, waves that have longer wavelengths will need a bigger shift or a bigger path length difference before they line up again, crest and crest. So the bigger the wavelength of the light, the farther from the central maximum the first bright spot will be. Y max also has a linear relationship with L. This is basic sort of screen geometry. You know that if a projector screen is far away, the points are further apart, and if the screen is closer, the points are closer together. The relationship that I think is maybe the trickiest one is that Y max has an inverse relationship with D. So when the slits are close to each other, that means that Y max gets really big as well. It's because the closer that the slits are, the waves basically are coming from almost the same spot. And so you have to go further away before we actually notice that the geometry makes a path length difference 1. We'll do a sample of this in class, so hopefully it will make more sense to you then. The last note is that each bright spot, or M order, is equally spaced. So as far above the central maximum as m equals 1 is, we're going to double that to get to m equals 2. So the equation then, if you would again pause the video, you can use these mathematical relationships to derive an equation for Y max at each bright spot M in terms of those three variables and any known constants. And then I'll unpause and we can take a look at what AP College Board thinks. So if it were me making this equation, it would look something like Y max equals M times lambda times L divided by D. If only it were that straightforward. College Board has, for some reason, put it all together in a very weird format to me that looks like this. B times Y max over L equals M over lambda. This is the same equation you just derived. It's just algebraically rearranged. If you solve for Y max, you'll see we have the same mathematical relationships. It's just in a different format. One little note about this equation, you'll see this says approximately equal to. This is called a small angle approximation. This works well as long as the screen is pretty far compared to the slit size, which is usually a pretty fair bet when we're talking about diffraction. But the geometry doesn't quite work out precisely if you don't make that assumption. You can also have more than two slits and get a similar diffraction pattern. If you have three slits or four slits or five slits, the pattern is basically the same. The bright spots end up actually at exactly the same locations. The one thing that's different is that the bright spots are slightly more defined. They look a little bit clearer. The difference in intensity is more dramatic when we have more slits. There is something known as a diffraction grating, which is essentially kind of like a polarizing filter, but a little bit different in that the slits are basically filling the entire screen. So the slits, there's more of them than the diameter of the light that's going through there. So the entire light is hitting slits. Diffraction grating just sort of takes this relationship to the max and acts like lots and lots of slits, and therefore the dots are produced very well defined. You don't have to do any new math with these. You can use the same math that we were doing with the two slit. Just realize that qualitatively they might ask you to describe the difference as you add more slits. The math is slightly different when we move down to one slit. And you can have diffraction with a single slit and create an interference pattern as well. The way this works is the wave actually kind of curls around the edges of that boundary. When there's a single slit, it's called an aperture or an opening, and the edges of the aperture act as your two wave sources. You can see in this picture that central maximum very clearly, well defined, really, really dramatic wave crests and troughs straight up the middle. But you can also see these gray stripes, right? Those are going to be your regions of destructive interference, and you can see some dimmer constructive interference built in there too. So that interference is happening from the waves that are created on the edges of the aperture. Compared to multi-slit diffraction, the central maximum is brighter and wider. Most of the wave energy goes straight through, and so we end up with a high intensity wave right in the middle, and the other bright and dim fringes are less defined. There is a different equation for one slit diffraction. I'm not going to derive it because the math is actually quite a bit more complicated than the two slit, but the equation ends up looking pretty similar. The main difference is that we have a variable A that represents the aperture size or the opening of the single slit. And instead of calculating Y max or the distance from the central maximum to the maximum, the next order maximum, this equation calculates the distance from the central maximum to the first destructive dim spot, so Y minimum. All right, we've reached the end of this video. Thanks for watching, and I'll see you in class.